the Chapter 11 quiz. There are 5 questions, 10 points total, just like usual. One of those questions is going to be a molarity to molality conversion. So just like we did in class about a week ago, this can be molarity to molality or vice versa. The big key there is how you manipulate that denominator. The middle of this is going to be related to these concepts that we talked about today or on Friday. Determining molality of a solution from experimental data, using that molality to determine the freezing point and the boiling point of a solution. So there's 3 questions there. There are 3 calculations there as well. Now, the important thing with this particular set of questions, especially the last 2, remember, the equation that you're given helps you to find the change in temperature. If we're actually determining the boiling point and the freezing point, we need to apply that change to the boiling point and to the freezing point. Meaning, if I get a delta T value, delta TB of 2 degrees, I need to add that 2 degrees to the existing boiling point to get the actual boiling point of the solution. Remember, the equation tells us the elevation of boiling point, how much higher it is than normal. And same thing on the freezing side. The equation tells us how much the freezing point's been depressed. So I need to subtract that value from the existing freezing point to get the actual freezing point. And then the last question concerns Raoult's law. So given some experimental data, can you determine what the vapor pressure of the solution will be? And so it's for these reasons, since we've talked about all of these concepts already, that's why I have no problem with us taking the quiz on Wednesday, because we've seen all of these already in some form or another. It's the other parts that we have to concern ourselves with. And so we'll go through those other parts today. We'll do things like applying the Van Hoff coefficient. We'll do things like, we'll talk about osmotic pressure, which will probably be part of your exam next Monday, but it's not going to be on the quiz. You got to remember, with the quizzes, we have to do some version of self-editing. We can't put every single concept on every quiz because a lot of times there are just too many. So we chose these ones because they're kind of the most straightforward, and we've had the most opportunity to talk about them. We have post-lecture activities over all of those. So that's the structure of the quiz itself. Any questions that I can answer for you about that quiz before we kind of wrap up on Chapter 11 itself? All right, so we're over here then. We started to look at example 6 on Friday. And after we looked at example 6, we kind of went into a little side tangent about the Van Hoff factor, because the Van Hoff factor is an important part of this particular study. Now, since calcium chloride is an ionic compound, we have to take into consideration its Van Hoff factor. Remember that the Van Hoff factor is equal to the number of particles per molecule dissolved. Which for calcium chloride would be equal to 3, because I'd have the calcium ion and I would have 2 chloride ions. That's where my total factor of 3 is. Now, this estimation is just that. We can see that we are actually given a Van Hoff factor here for the saturated solution of 2.5. And so what that means is that once we get to a certain concentration, it actually becomes more difficult for all of the ions to dissociate. And so what we end up getting is an average of 2.5 ions per molecule. So some will end up staying together in units while most of the others dissociate. How does the Van Hoff factor impact our equations? Well, it does so in the following way. The Van Hoff factor is often given by the lowercase letter I. And so how it impacts is we multiply that Van Hoff factor by the rest of our equation. So that equation that I gave you, delta TF is equal to KF times M. Well, in order to account for ionic compounds, we actually throw in that Van Hoff factor in there as well. So delta TF is equal to I times KF times M. Now we've got the value of I, 2.5. We've got the value of KF, 1.86 degrees Celsius per molal. The only thing that we're missing is the molality. And in this case, since we are using solubility data, it's actually not that difficult to get to that either. Remember, molality is moles of calcium chloride per kilogram of water. Well, we're already told we've got 70 grams of calcium chloride per 100 grams of water. So all that we really need to do is need to turn that 70 grams of calcium chloride into moles. 70.0 grams of calcium chloride. Molar mass of calcium chloride, 40.08 for the calcium, 35.45 for the chlorine times 2 is 110.98. So this would be 0.631 moles divided by 0.1000 kilograms would be 6.31 molal calcium chloride. Now that I've got that information, my I is 2.5, my KF is 1.86 degrees Celsius per molal, and my molality is 6.31 molal. 0.631 times 2.5 times 1.86 would give me 29 degrees Celsius. So my change in freezing point is 29 degrees Celsius. Well, since the freezing point of water is 0, my freezing point for the solution would be 0 minus 29, negative 29 degrees Celsius. So could calcium chloride melt ice at negative 20 Celsius? Absolutely. It can actually melt it all the way down to negative 29. But you can see, without that Hoff factor there, if we had just taken the freezing point depression constant and the molality and multiplied them together, we wouldn't have come up with 29 degrees. We'd have come up with something about 10, 11 degrees. The total ionic strength coming from those ions splitting off from the main molecule does have an impact on the overall concentration, does have an impact overall on the ability of that substance to dissolve and to lower the freezing point or raise the boiling point. All right. Any questions with number 6 here? All right, let's do this one together as well. What is the boiling point of seawater in which the concentration of sea salts is equivalent to 0.560 moles of sodium chloride per kilogram of water, and the Hoff factor is 1.85. So what we can draw out of this, this 0.560 moles of NaCl per kilogram, that is already a molality. We've got moles of solute per kilogram of solvent. That's molality. We also have a Hoff factor of 1.85. Again, we would estimate the Hoff factor here to be 2 because 1 sodium ion and 1 chloride ion makes 2 ions in total. Understanding that at higher concentrations, we're not going to get the full power of that complete dissociation. So the equation here, delta TB is equal to I times KB times molality. My I here is 1.85. KB for water, it's not given here. It's on one of the previous slides. It's 0.51 degrees Celsius per molal. And the molality here is 0.560. So if I take that 1.85, multiply it by 0.51, multiply it by 0.560 to 2 significant figures, I get 0.53 degrees Celsius. So that's how much the boiling point has increased. Remember, to find the true boiling point, I'm going to have to add that to the normal boiling point of water, which is 100. So 100 plus 0.53 would be 100.53 degrees Celsius. Remember that on the Celsius scale, the boiling points and freezing points are fixed values. They are not estimated. They are defined. The boiling point of water is defined at exactly 100 degrees. The freezing point of water is defined at exactly 0 degrees. So from that standpoint, they have infinite number of significant figures. We don't have to worry about rounding if the solvent is water. Now, if the solvent is something else, then we have to worry about how many decimal places were given for that freezing point or that boiling point. But if it's aqueous, understand that they are exact. And from that standpoint, whatever sig figs we get out of the equation, we just tack those on to the freezing point or the boiling point. All right. Any questions with number 7? All right, so let's move into our last colligative property. And that last colligative property is something called osmosis. Now, if you're in biology class, or if you remember from high school, you've heard of osmosis. Osmosis is the transfer of water across a semi-permeable membrane from an area of high concentration to low concentration. So if I have two solutions that are separated by some kind of a barrier that allows certain kinds of molecules through, like water because it's small, but blocks other kinds of materials from passing through because of their size, like salts or larger molecules, then what I will see is that the water will go from one side that is higher in concentration of water, that is more dilute, to the side that is more concentrated in terms of solute. And this process occurs naturally on its own. It does not require any outside interference from us. The only outside interference that we might provide is the semi-permeable membrane itself. Although in a lot of biological systems, the system itself provides that membrane. Your cell membrane, for example, in all of your cells is a semi-permeable membrane. Certain materials are allowed in, certain materials are blocked out. Your cells have other ways of transmitting salt particles or other kinds of materials from the inside and the outside of the cell. You get into those processes like potassium pumps or other kinds of active and passive transport in cells that you can get into in a biology class. Well, with this movement of particles from one side to the other, we know that there's going to be a natural progression that the solution on one side, let me just draw us a picture here to try to help us visualize this. Let's say that I've got a solution here and I've got it separated by this membrane. On one side, I've got a whole bunch of solute. On the other side, I don't have very much. Osmosis tells us that the movement of water would be in this direction toward the more concentrated side in an attempt to make it more dilute. And so what we see is that this natural movement would be going from left to right, from lower concentration of solute to higher concentration of solute, or higher concentration of water to lower concentration of water. Well, osmotic pressure would be, let's say that I introduce some kind of a object in here that's going to start pushing back. And that object pushing back stops the flow of this water. Whatever pressure that was that I exerted, that would be equal to the osmotic pressure of the solution. Now, we can calculate that osmotic pressure using three factors. And actually, if we want to throw in the Hoff factor, because it is relevant in here as well, it becomes four factors, because the M that we're talking about here is something called total molar concentration. Total molar concentration is molarity times the Van Hoff coefficient. So osmotic pressure, we can calculate it as the molarity multiplied by the Van Hoff coefficient times R, the universal gas constant, and T, the absolute temperature in Kelvin. Now for R, there are two primary values that we will use. There is one for a pressure unit known as atmospheres. R is equal to 0.08206 liters times atmospheres over moles times Kelvin. That is the entire unit. So that little fraction of 4 units is the unit for R. The other possibility is this one, where R is equal to 62.36 liters times millimeters of mercury per mole times Kelvin. So notice that only thing that changed in either of those units was the pressure unit itself, atmospheres or millimeters of mercury. That's really the only difference between those two units there. Everything else is exactly the same. And if you take the molarity, moles over liters, times you'll see that all of the units end up canceling with the exception of the pressure unit. That's where we get our pressure for pi, the osmotic pressure. So there is a method to this, kind of madness in terms of the equation, in terms of that unit for the universal gas constant, as to why this works. So that's osmotic pressure. Again, we can quantify it using this equation. Let's go ahead and take a look at an example of this kind of work in action. So here's a little bit more sophisticated of a drawing. In the chemistry lab, this particular apparatus is what we call a U-tube. I think you can kind of figure out why. And what we see in this U-tube is that if I have seawater on one side that is very brackish, very high in concentration of salt, very low in concentration of water, and I have normal saline solution on the other side, we're going to see a net movement of water from right to left here. And as a result, if unchecked, we would get a net overall change where the one water level is going to be higher than the other due to that movement of water. The osmotic pressure would be how much force do I need to push down on this side to get those levels to even up again. And so, as I mentioned before, the Hoff factor does play a role in here, especially for our ionic substances, our ionic solutions. I did neglect one unit of R, and it is this bottom one. The reason I left it out is because it is exactly the same as the one above it. Millimeters of mercury and torr are the same pressure unit. We sometimes refer to millimeters of mercury as torr as kind of a hat tip, a nod to the person who invented the barometer, Evangelista Torricelli. And so the unit of millimeters of mercury is in some places renamed torrs or torricellis in his honor. And that's where that comes from. They are the same thing. And so if you see torr, understand that millimeters of mercury are the same thing. All right, let's do an example. If the total concentration inside of a red blood cell is 0.310 molar, what is the osmotic pressure of this fluid at body temperature? We are told to assume that the membrane surrounding the cell is semi-permeable. Well, the thing to note here, we are told that this is a total concentration, which means that we've already rolled in the Hoff factor into our molarity. So this is both together. So pi osmotic pressure is equal to IMRT. I times M, we have already been told, is 0.310 moles per liter. That's what molarity is. The pressure unit that we use really doesn't matter. We'll use torr here just for the sake of it. Liters times torr over moles times Kelvin. 37 Celsius, 37 plus 273 would give me 310 Kelvin. My moles cancel, my liters cancel, my Kelvin cancel. All that I'm left with are torrs. 0.310 times 62.36 times 310 to three significant figures is 5,990 torr of pressure. Now keep in mind, atmospheric pressure is about 760 torr. So this is just a little bit under 8 times that. And this is out of a 0.31 molar solution. So one thing that is really interesting about osmotic pressure is that we can get very measurable numbers from very dilute solutions. Because you got to think about this. This was a 0.3 molar solution. How many times have we worked with solutions that were at or near that concentration over the course of our semesters? And yet it produces an osmotic pressure that's nearly 8 times atmospheric pressure, easily measurable. In fact, probably a little bit tough just using some of the equipment that we have in terms of pressure. That's a lot of pressure to hold. All right, any questions with example 8? All right, so I'll leave you to read this kind of information on your own. It's kind of interesting as far as looking at what environment effects have on things like your cells. So looking at, what does your body environment do to your cells if your environment starts to get out of whack? So this is what your red blood cells should look like. And if we change conditions by either making the solution around them too dilute or making the solution around them too salty, they can actually have some pretty drastic effects on the cells and their function as well. Another application we see for osmotic pressure is in the desalination process of seawater. So in particular for countries that do not have access to fresh water, but have access to ocean or other brackish water sources, desalination is a process that can be done. There are a number of ways to do desalination. One of them is distillation, but that's pretty difficult to do because distillation requires a ton of energy and it strips the water of any minerality. You'd have to put mineral back into it. So reverse osmosis is a process that most of you are familiar with already. If you drink bottled water at all, most bottled water goes through at least one, if not several, reverse osmosis processes for the sake of cleaning it up and purifying it. And that process looks something like this. Inside of these tubes are all semi-permeable membranes. And so what happens is that they pump water through these larger tubes, but they do it in a high enough pressure that basically the process of osmosis gets reversed. So if you take osmotic pressure, remember, osmotic pressure stops the flow of water from one direction to the other. What this would do is, if we increase that pressure, if we go beyond osmotic pressure, then we can start to force the water to go from the impure side to the pure side. Because remember, the net flow wants to go the other way. We want to go from pure to impure to try to make that side more dilute. If I put enough pressure on it, we'll actually take the impure, push it through that membrane, and we get pure water coming through on the other side. This is how companies like Aquafina take tap water, run it through a filter about 5-6 times, and then sell it to you as purified water. All they did was just take tap water and run it through a reverse osmosis pump a couple of times. But in the process, they got rid of some of the impurities that are in that tap water, and they can sell it to you at a premium by calling it, purified water. And obviously Aquafina is not the only one that does that. They're just, they've been the most honest about what their sourcing is. But most processes involve some kind of reverse osmosis kind of process. Now, there's one other thing that we can do, and it spotlights something that I highlighted just briefly. Because osmotic pressure gives us very measurable pressures at very low concentrations, we can actually use that data to help figure out molar masses of unknowns. And we can do so because it doesn't require a whole lot of substance, which when you're doing unknown analysis is a really big benefit. A lot of times when you're doing unknown analysis, you may only have milligrams of the substance to work with. And so this allows those people to actually go after and do some analysis with these larger samples without having to use a larger sample. And so I will actually there are 2 practice problems regarding that concept. I'm going to throw them into a lecture supplemental in a separate video just because I've got 2 minutes. And so look for that to come out sometime later today as well. But what I'm going to do is we're going to cap this off by talking about another solubility concept. And this is something called Henry's Law. Now, Henry's Law is not something that you need to worry about as far as quantitative measurement is concerned. I don't need you to know what this equation is or how to use it. I just want you to know that it exists, and it does give a definitive relationship between the concentration of gas dissolved in a liquid and the pressure of the gas above the liquid. And so when it comes to gas solubility, there are really two things that you need to be aware of. One of them is that concentration and pressure are directly related to each other. If the pressure above a liquid is higher, the gas solubility in that liquid is higher as well. The second thing that you need to know is that solubility of a gas overall generally depends on temperature. The colder the liquid is, the more likely that substances, that gases will be able to dissolve in it. And this is kind of backwards from a lot of our thinking. We tend to think of high temperature, high solubility. But in the cases of gases, that high temperature actually creates a problem because the high kinetic energy that already exists inside of gas molecules gets exacerbated by the high kinetic energy of the water molecules, and it makes it much more easy for the gas molecules to escape. So when it comes to gas solubility, we tend to think of two factors: cold solution and high pressure above the solution. And probably the easiest example that I can think of that manifests both of those concepts very, very well in one convenient package is this. A bottle of soda, a can of seltzer water, whatever you want to think of. Carbonated beverages are packed under high pressure. The reason why? To get that carbon dioxide to dissolve in the liquid. Carbonated beverages are best served cold. Why? They go flat pretty quick if they're warm. And if you think about what you see when you open a carbonated beverage, first thing that you see, you get that hissing sound as soon as you open it. Why the hissing sound? You're releasing the pressure that the whole thing was kind of holding on together. And the other thing that you see as soon as you open that, as soon as you hear that hissing sound, all those bubbles start to come up, because now that the pressure above has been released, the concentration inside of the liquid is going to go down because the pressure is now lower. And so you see all those bubbles rush up as a result. And so think about this. When is your soda the fizziest? When it's cold. When is it fizziest? After it's first opened or after it's sat out for a while? Obviously after it's first opened. And it has everything to do with those two factors, temperature and pressure. That's all I have for today. Have a good afternoon. I'll see you on Wednesday.
I have a really quick question about lab. Is there a quiz for molar mass of a volatile liquid?